So before we actually graph, let's talk about the letters up here. So at least kind of know what the letters are, what they mean. Okay. So the number in front of cotangent, and this one is very similar to, I think, number 14 from your homework. 27? 27, okay. So cotangent, A is 1/4. That A only helps us get a second point to stretch the graph. It's not the amplitude. There is no amplitude. So even though there's an A value, there is never an amplitude because there's not a max. So the amplitude stretches us to the max. Well, there is no max. So yes, there's an A value. Yes, we're going to use that, but there is no amplitude. What's B? 1. The number in front of X is B, and that's just a 1. That helps us find the period, which is the distance from an asymptote to another asymptote. Well, with tangent and cotangent, Colin, the period is just pi instead of 2 pi. So here our period would be pi over 1, which is just pi. So from one asymptote to the next, that distance should be pi in between our two asymptotes. And then the third letter that's up here is a C, and that C is pi over 2. That is our phase shift. But these graphs are a little different because they don't necessarily start at 0. So I can't say that it's shifting based off of the 0 value. So we don't really necessarily have a point that's shifting. We're going to have asymptotes that shift. So to find out the shift of our graph, we're going to focus on the asymptotes. So we're going to take whatever's in parentheses or whatever's after cotangent. And in this case, it's x minus pi over 2. And you're going to set that equal to where one asymptote typically is for cotangent. So does anybody know where an asymptote usually is for a cotangent graph? Dylan? Negative pi. I don't know why I made that squiggly. So this is where a typical asymptote is. We're going to see how the pi over 2, the C value, affects that. Then we're going to do the same thing with another typical asymptote. Dylan, where would another asymptote be for cotangent? 0. And then Dylan, the third asymptote for cotangent is at pi. So these three numbers here represent the normal asymptotes for cotangent. That's where those three asymptotes usually are located. This is what's shifting. The asymptotes are shifting. They're going to move. So in order to figure out where they go, you solve for x. So you're going to take the pi over 2 to the other side, and Dylan, negative pi plus pi over 2 is negative pi over 2. So I'm shifting pi over 2 from the original asymptote. So it still is a phase shift, but we're shifting from the asymptote. The next one, Dylan, would be at pi over 2, and then Dylan, our last one would be at 3 pi over 2. So with tangent and cotangent, we're really focusing on the asymptotes of the graph. Where are they located? Question. So again, we're using the original asymptotes and then finding the new ones. So now we're going to see if we can graph this. And we have pi over 2. They're all pi over 2 values. So I'm going to just go over 2 blocks and call that negative pi over 2. Just so it's not all squished together. We have a whole bunch of space here, so just trying to give us some space. So 2 blocks represent pi over 2. So if I go over 2 more on the other side, that's still pi over 2. 2 more would be pi. 2 more would be 3 pi over 2. And you can stop once you have all your asymptotes represented. So again, I just used 2 blocks to kind of spread apart the graph a little bit so that it wasn't all squished together. Any questions so far? After we have the graph labeled, we'll go up 4 for the y. We're going to place those asymptotes on the graph. That's one of the most important parts. The asymptotes, the second part would be the intercepts. So the asymptote we have calculated to be at negative pi over 2. That's that dashed line, positive pi over 2. And then 3 pi over 2. Okay, so we have 3 asymptotes. Where would the intercepts go? Where's an x-intercept going to be located? Home. At pi. So one x-intercept is at pi. It'll always be in the middle of your asymptotes. Because these asymptotes are, like, everything is occurring at one of the 90-degree angles. So we have like a 0, pi over 2, pi, 3 pi over 2. So everything is still with that unit circle that we originally were talking about. Another x-intercept, Dylan, would be at 0, 0. And then the last thing we're going to use is that a value. We have 2 other points that we're going to graph. And that a value helps us plot that other point, and it's 1/4. So in between your x-intercept and your asymptote is going to be a final point. In between your x-intercept and the asymptote on another side is also a final point, so that we kind of have a stretch of the graph. Cotangent, is it increasing or decreasing when you look at the graph from left to right? Decreasing. So cotangent goes down, tangent goes up. They're reciprocal functions. So the one goes down, the other one goes up because they're opposites. So if it's decreasing, my a value is 1/4. Usually I would go up to 1, but I'm only going up 1/4 of that. So I would just go up to 1/4. So I counted by 4, so it worked out nicely. On the other side, I would go down to 1/4 so that I have a decreasing tangent graph. So these 2 values here gives me the stretch of the graph so I know where to connect it. So sometimes the values are high and we stretch up high to get to connect those points. And then I repeat that for the next intercept and asymptote. So it's a decreasing function, so up 1/4 and down 1/4. So now I have 2 periods of a cotangent function. And everything is based off the asymptotes. So you're finding the asymptotes from the original 3. And we'll always have 3. For tangent, I have 3 different ones. For cotangent, we have the negative pi, the 0, and the pi. So these guys here, that's the important part of the graphs for tangent and cotangent. Questions? Does that help a little bit with the last 2 problems of homework? Is there another problem from the homework you wanted to go over? You sure?
Yeah.
Okay.
I know you were waiting.
Okay. All right, so today we are going to look at graphing secant and cosecant. But before we do that, if you can flip to page 3 of your packet. And if you have a device out, just take a quick picture of it so that we don't have to flip back and forth. We're not going to graph all of the points. We're going to refer to a couple of important points. So if you have something out, take a picture of that chart. We're going to just kind of refer to that chart, and then we don't have to flip back and forth, back and forth, back and forth, back and forth. That's annoying. So I think it's page 3, right? Yeah. Yep.
Did you do the cosecant and secant last night for homework? Bro! Get out.
I used to have that.
You're wasting my time. If you need a copy of it.
That's a, he's going to be able to mentally figure it out.
I feel like it's not that hard, yeah.
You just divide the answer by okay. Or you divide
Just
one
take
by
all
the
the
answer.
values.
There you go, yeah.
Yeah, it's not.
All right, so now that you have a little picture of that, if you can go back in your packet to page 37.
Dylan.
So go back to page 37. And on page 37, we have secant and cosecant. Cosecant is first, and then we have our secant graph. And what we're going to do is we're going to first label it like we've labeled every other So on our x-axis, go over 3. Call that pi over 2. If you prefer to label it below, label it below. Wherever you want to label it. I'm going to just label the secant as well so that they're both labeled. So the labeling is the same for each initial graph. So what I'd like you to do is graph sine. So our first graph is cosecant. Cosecant and sine are reciprocal functions. So I want you to plot some points for sine. So back in your memory bank, sine starts at 0, 0. It goes up, back to normal, down, and ends at normal. And I'd like you to dash this in. So just dash it in or lightly sketch it in. I'm going to do the other side as well. So this is our sine graph. So looking at your chart that you just took a picture of, if we have the sine being 0 and the cosecant is its reciprocal, what happens to cosecant at the angle 0? So what happens when you take a reciprocal? So if the cosecant is, or the sine is 0, it would be undefined. So on your chart, if the sine is 0, to find cosecant, you have to take 1 over sine. So remember, the cosecant of an angle is 1 over the sine. Well, if sine is 0, now I have 1 over 0. So at the angle 0, it's undefined, and we know undefined means you have an asymptote in the graph. So if sine is undefined, if sine is 0, my cosecant is undefined. Hannah, where else on your chart would the cosecant be undefined? Yeah, at all the places where sine is 0. So if you look at the graph, any place where sine is 0, the cosecant is going to be undefined, which is every x-intercept. So every x-intercept, we have asymptotes. So x-intercepts of sine force cosecant to be undefined because we're taking 1 over 0. All right, we're going to try and plot a couple other points. If you can go to, on your chart, the angle of pi over 2. Brenton, do you have pi over 2 on your chart? What is, do you have the cosecant for pi over 2? It's, 1, because the sine is 1. 1 over 1 is 1. So the cosecant is 1. The other points that we're going to plot would be when when the sine is equal to 1/2. So Brenton, on your chart, when do you have a 1/2 for sine? What angle? Yeah. Okay. And what happens with the cosecant if sine is 1/2? Oh, okay. Pi over 6. Okay, so at pi over 6, the sine is 1/2, which looks right about here. So if sine is 1/2, what's the cosecant going to be? 2. So I'm going to have a point up here at 2 when the sine is 1/2. And over on the other side, I'm going to have that same point when the sine is 1/2. So a cosecant graph goes the opposite of my sine graph because they're reciprocals. So if you have a 1/2 for sine, the reciprocal of it is 2. So it's going the opposite direction. A decimal, when you take the reciprocal, actually gets bigger. So this is one piece now of my sine graph. If you go to the next one, just moving to the right, what do you think this part is going to look like? It's going to be a parabola, Colin, but it's going to go, yeah, it's going to go down. So I'm still going to have a parabola, but now it's going the other direction. So I have these little bounded parabolas that go the opposite direction of the sine because they're reciprocals. So it's looking like an open up parabola, kind of going the opposite direction of sine. So if I continue that on the other side, wherever sine is 1 is where my cosecant graph starts, and it goes the other way. So the cosecant graph is going down. And then again, whenever my sine is 1, that's the point for my cosecant graph, and it goes up. So the cosecant graph are really 4 kind of bounded parabolas. Because they're not going to get wide, because there's the asymptotes there forcing it to stop at a certain value. So when we graph cosecant, we're really going to graph sine. We're going to use the max and the min of sine to finish our graph. So graphing cosecant is really no different than graphing sine. We'll sketch in a little sine curve, and then we'll finish the cosecant. Questions? So see if you can graph a cosine. So we're really thinking, let's graph cosine first because they're reciprocals. So Carrie, the first point for cosine is 0, 1. So cosine starts up high where sine starts in the middle. And remember, cosine goes down and then it comes back up. It ends where it started, up high. And then on the other side, doing the same thing. It goes down and comes back up. So you might not have to use the chart. If you look at your, oh, I was supposed to not connect them, but that's okay. I wanted to make it dashed. No, happens. There we go. So where do you think an asymptote would be for secant? The x-intercept. So go to your current graph for cosine, find an x-intercept, and make an asymptote. So asymptote at the x-intercepts. Because if the cosine is 0, 1 over 0 is undefined. So x-intercepts. Now make asymptotes for our graph. All right, so what else do you think we would graph? Yeah, there's a little kind of parabola thingy. So go to a max. That becomes the min of cosine. So if it's a max of sine, it's now a min of the, secant. If it's a max of cosine, it's the min of the secant. So that creates kind of like a little parabola. So they share the same point of 1, 1. Or, sorry, the y value 1. But they're never going to share that max or min point. They are connected. Go to a min, and again, draw in your secant. And I have another min over here, and so technically there are these two leftover pieces, and really we just have like half of a parabola connecting those extra little pieces. So asymptotes are at x-intercepts. A max of cosine is actually the min of the secant. Same thing with the sine and the cosecant. Questions?
They asked you to do like a domain, would you start at like bracket -2 pi?
For this one, yes, we would. If we were just giving the domain of what we see, you would have a bracket at -2 pi. So if we were giving the domain, it would have to, yes, based off of what we have drawn, yes. But it's from one asymptote to the next.
Let's not do that.
The range of these graphs would go from 1 to infinity. So if we were thinking about the range, it starts at 1 to infinity. This guy goes from -infinity to -1. So the range would be a little different. If these graphs go to infinity, remember there's no amplitude. So the only two graphs that have an amplitude are sine and cosine. The other four don't because they go to infinity. Any graph that goes to infinity doesn't have like a stopping point. It's just going forever. So amplitude is the stretch from the center to the top. Well, there isn't a top because they go on forever. Questions? So we're going to try and graph a cosecant or a secant function. I can't remember. I think there's both in here. We'll just start with, we'll start with the cosecant. We're going to try and graph this. This should be in the middle of the back, I think. It's the second problem on the back. So when we graph this, we're going to pretend to graph its reciprocal function. So let's see. So Nick, if you have cosecant, what's reciprocals with cosecant? What function goes with the cosecant? What's its partner?
The cosine. Wait, what? So, the sine.
The sine. So if we have cosecant, we are really going to graph 2 sine x plus pi over 4. So cosecant and sine are reciprocals. The secant and the cosine are reciprocals. So we're actually going to graph sine. We're not going to graph cosecant. We'll graph sine first. So if I were graphing sine, the A value is 2. Nick, the B value is 1. And then Nick, what's C?
Oh God. Negative pi over 4.
Perfect. Negative pi over 4. Good. All right. So going back, let's get the period. Remember, we're graphing sine. So Brenton, the period for sine is usually 2 pi. So 2 pi over 1 is just 2 pi. Brenton, how do we get our key points so that we know how to count? Yeah. So we take 2 pi over 4, so we're going to count by pi over 2. So we're finding just the regular stuff that we found for sine. The last thing that we need is the phase shift so that we know where to begin this graph. Again, this is different from tangent and cotangent. Tangent and cotangent are like the only ones that are kind of separate, focusing on those asymptotes. Remember, the phase shift is C over B. Well, that's just negative pi over 4. So right here is where our graph starts. That's the first angle that we're going to graph, negative pi over 4. So going back, thinking about graphing sine, negative pi over 4 would be the first x value, or the first angle. Does anybody remember how you get to the next one? Garrett? Yeah, perfect. We're going to add pi over 2, which is really 2 pi over 4. So Garrett, the next angle would be?
3 pi over 4, or no, 1 pi.
Yeah. And then we would have 3 pi over 4. So continue adding pi over 2, or 2 pi over 4. So we would have 5 pi over 4. And then we would end at 7 pi over 4. So remember, the period's 2 pi. So from negative pi over 4 to 7 pi over 4, that distance is 2 pi. All right, the last thing we need then is to worry about y. There's an a value of 2. Its sign usually starts at 0, goes to 1, back to 0, down to negative 1, and back at 0. So Hannah, how do the y values change if there's a 2 in front of sign? Yeah. So you're multiplying the original y values by 2. So now we have a 0, a 2, a 0, a negative 2, and then a 0. So if everything is a pi over 4, probably should count by pi over 4. Makes sense. So 2 pi over 3, yeah. But however you want it. If you want to go over 2 boxes, that's fine. Yeah. You can draw extras. So I counted by pi over 4, and I just left each box represent pi over 4. If you wanted to go over 2 spaces to spread it out a little more, I think you just need a couple extra lines on the right side of your graph. And then we're going to plot the 5 key points. And when you connect it, make it a dashed line, because this truly isn't our end answer. We're just using the graph so that we can then graph the cosecant. So our first point, we shifted to the right, or I'm sorry, to the left at negative pi over 4. There was a phase shift, so our first point is at negative pi over 4, 0. And then we're at positive pi over 4 and all the way up at 2. So again, when you connect your points for sine, dash that in, because it's truly not our graph. It's not the end graph. We're using it to help us graph the cosecant. So sine is that hill and valley. After you have the sine, find your asymptotes. So Carrie, how do you know where an asymptote is located after we have our sine graph? Any x-intercepts. So go to an x-intercept after your sine graph is complete. And an x-intercept then forces your cosecant to be undefined because the sine is 0. So x-intercepts are now asymptotes for our cosecant graph. And then any max point is still a point for cosecant, but it really is the minimum of this kind of bounded parabolic shape. So max becomes the min, and then we draw in our little curve that skims along the asymptotes. If it's a minimum for our sine, then it really is a maximum for our cosecant. Yeah, oh yeah. Questions? So what happens if there was a sinusoidal axis? What does the sinusoidal axis do to the graph? Yeah, it moves the graph up and down. So if there's a sinusoidal axis and it moves the graph up or down, that's like your new x-axis where it's going to be undefined. So whatever points are on the sinusoidal axis is where your asymptotes are created. So if this did have like a +3 after it, or a +2 or a -1, that sinusoidal axis is like the x-axis where your x-intercepts would faux x-intercepts. But that's where your asymptotes would be created. So where you have points on the sinusoidal axis creates an asymptote for our function. Questions? So tonight you're graphing secant and cosecant. There are 7, so if you did grab 2 pieces of graph paper, you still probably have an extra one left over on last night's. But really you're graphing sine and cosine. So sketch in sine and cosine, and then get your asymptotes, and then the rest of the graph for secant or cosecant. Questions? Oh, this. Yeah.
We don't get through I did, I wanted to leave off.
Why did you have me off?
Because I was going off, if we're in the parking lot, people like, places, you know, we play.
What? Acting is such a crap. That's what I did.
I go